In this video lesson, we're going to be talking about the three subatomic particles, that is, protons, neutrons, and electrons. We'll be talking about how you can determine the quantity of protons, neutrons, and electrons within an atom, as well as towards the end of the video, we'll be talking about isotopes and ions and how those different types of atoms affect the number of subatomic particles. By now, you should have a general idea of protons, neutrons, and electrons. I would like you to note the relative charge that each one contributes, the location, as well as what their contribution to the atom is. Before we move on, it'll be a good idea to have a basic understanding of how we can determine the number of protons, neutrons, and electrons. So, let's start with a proton. The proton's the easiest. The proton is going to be the atomic number of a particular element. It's important to know that it's the number of protons that determines the element that you're looking at. For neutrons, neutrons can be found by looking at the mass number. You see, the mass number is the sum of how many protons plus how many neutrons a particular atom has. So neutrons can be found by taking the mass number and subtracting the number of protons out of it. Finally, electrons. If you have a neutral atom, electrons is going to be equal to your number of protons because the positives always have to equal out the negatives. When we get into isotopes and ions, we'll see how these numbers change, but for right now, this is good enough. Isotope notation. So this is what's called isotope notation. On the left side of the screen, you'll see a basic square that you would see on a periodic table. You'll notice some bits of information. We see that it gives us the element name, the element symbol, but more importantly, it gives us these numbers. You have a whole number, and then you have a decimal number. The whole number is the atomic number for the atom. Remember, it's the atomic number that not only tells us how many protons we have, but it also tells us what element we're looking at. Every element has its own unique atomic number. The decimal number that's at the very bottom is called the atomic mass, or maybe more specifically, the average atomic mass. What we'll discover is that there's lots of different atoms out there that are the same element but have different masses, and therefore this number reports to us the average. Now, we oftentimes write that in isotope notation, which is what you see here to the right. What you'll notice is that the element symbol will be written here. There's a big number on top, and then there's a smaller number on the bottom. The big number on top, which is represented by the letter A, is going to be your mass number. The mass number is always a whole number because it represents the number of protons and number of neutrons together that this particular atom has. The number on the bottom, which is represented by the letter Z, is the atomic number, and this is just going to be the number of protons. Now, two things I'd like to note. First of all, most people would think the atomic number is the letter A, but it's not. It's the letter Z, so that can be confusing. And second of all, look at these numbers, or these quantities that are on the right. The mass number is the number of protons and neutrons total. Remember, it's the protons and neutrons that contribute to the mass. On the bottom, it's just the number of protons. So if you wanted to determine what's the number of neutrons, you would just take the mass number minus the atomic number, and this would give you your number of neutrons. We'll be looking at some practice of this in just a few slides. All right, let's go ahead and do a quick check for understanding to make sure we understood what we just went through. Write the isotope notation for the following elements. The first thing I'm going to do is I'm going to look up the element symbol. Silver is the symbol Ag. Now, I have the two numbers that I need to write on the side. Remember, the top number is going to be the mass number. Now, silver has an average atomic mass of approximately 107.87. We're assuming that we're dealing with an atom that's going to be close to the average, and therefore we're going to round the average atomic mass found on the periodic table to the nearest whole number, because remember, the mass number is always a whole number. So 107.87 is going to round up to 108. And then the number that goes on the bottom, remember, is the mass number, the atomic number, or the number of protons. Silver is 47. If we look at chromium, chromium has the element symbol Cr. Once again, the average atomic mass for chromium is 52. And since that's pretty much spot on 52, that's the mass number that goes on the top. The atomic number for chromium is 24, and that gets written on the bottom. Now let's look at some situations where we have neutrons and electrons that may not be the same as what they would be in normal circumstances. First, let's talk about what an isotope is. Not all atoms of a given element are identical, as Dalton once predicted, but actually most elements on the periodic table have what's called 2 or more isotopes. An isotope is defined as atoms that have the same number of protons but a different number of neutrons. Because it's the same number of protons, this means that it's the same element. However, the element atoms weigh different, and the reason they have a different mass is because the number of neutrons are different. Let's take a look at a pictorial view of this. Let's take a look at hydrogen. A normal hydrogen atom has 1 proton, 1 electron because it's neutral, and 0 neutrons. However, look at the 2 drawings that are on the right. You'll notice they both have 1 proton, just like the first picture did. So all 3 of these are pictures of hydrogen. However, this middle picture has 1 neutron, and the picture on the far right has 2 neutrons. As a result, all 3 of these atoms would have a different mass, but all 3 are hydrogen because they all 3 have 1 proton. These are what we call isotopes of hydrogen. Notice the regular or normal version of hydrogen is simply called hydrogen, but the 2 isotopes that are on the right with different masses actually have special names, deuterium and tritium. Don't let that confuse you. Those are just special names for hydrogen isotopes. Alright, so what would those isotope notations look like? Let's write them below. I know all 3 of those are hydrogen, and so I'm going to go ahead and write H as my symbol. Because they're all hydrogen, they all 3 have an atomic number of 1, which is the number that gets written on the bottom. Remember, the top number is the mass number, and the mass number is always the number of protons plus the number of neutrons. In the first picture, there's 1 proton and 0 neutrons, and therefore the mass number would just be 1. In the second picture, the total number of protons and neutrons is 2, 1 proton and 1 neutron, and therefore the mass number for the second is 2. For the third picture, we see the number of protons and neutrons total is 3, 1 proton and 2 neutrons, and therefore the mass number is 3. This would be the isotope notation for all 3 of these atoms. The first one is the regular version of hydrogen, and the second 2 are isotopes. Now, there's a lot more isotopes than just that, and so we actually have a different naming convention we use when we're naming isotopes. We typically will name isotopes based after their mass number. So for example, if we were to look here, U stands for the element uranium, and 235 would stand for the mass number, and so we would call this uranium-235. You might be familiar with some other examples, such as carbon-12 and carbon-14, which is used for carbon dating. It's important to note that isotopes do behave like each other because they are the same element. They just happen to have a different mass. Now, when it comes to actually calculating the number of neutrons that a particular atom has, we need to keep these points in mind. If the mass number is not given in the problem, such as it was in our first 2 examples of silver and chromium, we will use the rounded atomic mass that's given from the periodic table. However, if the mass number is given, or if the problem is giving you number of protons and neutrons, like our last example did, we need to use that value instead of the periodic table. Once you do this, if you notice the mass number is different than what's on the periodic table, that's how you know you're dealing with an isotope. Let's go back a slide and take a look at how this works. You may remember that these were the 3 atoms that we drew from the previous slide. Now, if I were to look up on the periodic table at hydrogen and look at its atomic mass, it is roughly 1.008. If we rounded this to a whole number, it would be 1. So what this is telling me is that the average of the hydrogen atoms in nature would have a mass number of 1. Out of our 3 isotope notations that we drew, which one would that fit? The answer is the first one, because this is the mass number of 1. So this is what we would say is the normal version of a hydrogen atom. However, because 2 and 3 deviate from the normal 1 atomic mass that would normally appear on the periodic table, these 2 atoms of hydrogen we would say are the isotopes, because their mass numbers are different than what's on the periodic table. That also now leads us to ions. Isotopes were atoms of same number of protons but different number of neutrons. An ion, on the other hand, is now looking at an atom with a charge, not necessarily a change in mass. For this reason, we're looking at atoms that have the same number of protons but different number of electrons. It's very important to understand that ions, or atoms with charges, come from the electrons changing the amounts, not the protons. So for example, atoms that have positive charges, or called cations, come as a result of not gaining protons, but instead losing electrons. Because remember, electrons are negative particles. If you lose negative particles, you're going to become overall positive. However, negative ions, also called anions, means that electrons were gained. So charges come strictly from the number of electrons either gaining or losing, not protons. Here's a helpful equation if needed. The number of protons minus the charge of the atom is going to equal the number of electrons. So think about it. If an atom has 10 protons, but is neutral or has a zero charge, that means it's going to have 10 electrons, which we know to be true. However, if the charge is different, let's say, for example, we have an atom that has 10 protons and it has a charge of positive 2, that's going to give us 8 electrons. And you can see that if you see 10 protons and 8 electrons, you have an addition of, or a net charge of 2. Another example has been given down here. 8 protons minus a negative 2 charge would yield 10 electrons. 8 protons and 10 electrons would give a net charge of negative 2. So let's do some structural practice. You'll notice down here in the bottom right there is a key telling you which circles stand for neutrons, protons, and electrons. Pause the video and write the isotope notation for each of these 5 pictures. Then I will reveal the answers. Alright, take a look at the answers and see how you did. I would like to point out one, make sure you notice for letter D, this is actually an ion as well, because you have 3 protons in the middle, but 2 electrons, making it overall positive 1. Alright, in chemistry, a lot of times you're going to be asked to fill out a table that looks something like this. It'll give you some information and you'll have to fill in the missing parts. Let's go ahead through a couple and we'll see how we do, and then I'll let you do a couple on your own. Alright, let's look at the first one. All I know is that the first one has 16 protons and a charge of negative 2. I'm immediately going to put 16 in the atomic number because I know that the number of protons is always equal to the atomic number and vice versa. Alright, now I know that this also has a negative 2 charge. Remember, charge goes directly with the number of electrons. If the overall charge is negative 2, that means it has 2 extra electrons than it does protons. And therefore, if it has 16 protons, it must have 18 electrons. Alright, now I need to figure out what element it is we're looking at so I can fill out the rest of the information. If I look on the periodic table, element 16 is sulfur. Alright, now it doesn't give me the mass number, and it doesn't give me the number of neutrons that I could add to my protons to get the mass number. So, since it doesn't give us either of that information, we're going to fill out the mass number based on the average atomic mass given on the periodic table. If you were to look at sulfur on the periodic table, the average atomic mass is 32.07. Rounding that to the nearest whole number, that gives us a mass number of 32. To find the number of neutrons, I simply take my mass number minus my atomic number, or number of protons, which is the same thing, and that will give me my number of neutrons, which is 16. Finally, it has some yes or no questions on the side. Is this an ion? The question is yes, or the answer is yes, because there is a charge, negative 2. Is this an isotope? Well, since we use the mass number given on the periodic table, this would not be an isotope. Let's do one more together. I'm actually going to skip to the third one, so we can do that one together. Alright, I know that the mass number is 14, the atomic number is 6, and the charge is negative 4. Alright, since I know the atomic number is 6, immediately I know how many protons I have, which is also 6. Since the charge is negative 4, that means I have 4 extra electrons than I do protons. And so if I have 6 protons, that means I have 10 electrons. Now, how many neutrons do I have? Well, in this example, we're looking at element number 6, which is carbon. If you look up on carbon on the periodic table, you'll notice it has a mass of 12.01. However, this particular problem is telling me that this atom in particular has a mass of 14. Did we make a mistake? No, we didn't make a mistake. This element in particular, or excuse me, this atom in particular, must have a different mass than a normal carbon atom would. And so we need to use this number rather than the periodic table. So to find the number of neutrons, I'm going to do the mass number minus my number of protons, and that gives me my number of neutrons is 8. Finally, my yes or no questions. Is this atom an ion? The answer is yes, because it has a -4 charge. Is this atom an isotope? Well, normally a carbon atom would have a mass number of 12. But in this example, the mass number is 14, indicating that its number of neutrons is different. Because it differs than what's on the periodic table, it is also an isotope. Go ahead and pause the video and see how you do on the two that I've left blank. Then hit play to reveal the answer. Alright, here are the answers for the second and the fourth one that we skipped. Notice in the second one that since it didn't give us the number of neutrons or the mass number, we used what was on the periodic table, therefore it was not an isotope. However, in the last one, the mass number differed than what was on the periodic table for aluminum, which normally should have been 27. And so yes, it was an isotope. All four examples were ions because all four had charges. If the charge was neutral or 0, it would be no. Okay, let's give you one more last chance to practice. Do the practice that's on this page right here, and then hit play to reveal the answers. Alright, let's see how we did. In the first three, the answers are up here. Uranium was neutral, and therefore protons and electrons were the same amount. However, for selenium and iron, because they have charges of -2 and +3 respectively, their protons are different from their electrons. To find the number of neutrons, you simply had to subtract the mass numbers and the atomic numbers. For the last two down here, notice that there's no indication of charge. Remember, the -14 means that's the mass number, not -14. Same thing with iodine. So those answers are right here. And since there's no indication of a charge, notice the protons and the electrons are the same. It's very important that when you're looking at the number of neutrons, you have to go based off of the mass numbers that are given, not on the periodic table. The only time you use the average atomic mass from the periodic table is when they do not give you a mass number or when they don't give you number of protons and neutrons. For this last one down here, this might have been tricky. You may have been tempted to think that 66 was the atomic number, and you may have put the element that was 66 that was on the periodic table, which would have been dy. But that's not what it was asking. 114 is the mass number, 66 is the number of neutrons, so 114 minus 66 gives us the atomic number of 48. That is what identifies the element as cadmium, or Cd. The biggest mistakes that I see students make when they're doing practice problems like this is they oftentimes think that the number on top is the number of neutrons. Be careful, that's just telling you how many protons and neutrons together. So make sure you watch out for that. And the second mistake that I see is students want to use the average atomic mass that's listed on the periodic table instead of using the mass numbers that the problem gives you.